The next thing that we're going to discuss is the logarithm. When I say the word logarithm, a lot of us may not have heard that term before, right? But luckily, it's not too difficult to deal with, right? So the very basic, generic, everyday definition is going to be the inverse of an exponent. All right, what that really is basically saying is it's the function we're going to use to undo taking something to an exponent. All right, so down below, we have these considerations here. All right, if I told you x plus 2 equals 7, if I wanted to undo that plus 2, I would subtract 2. Right, and we end up with a solution of x is equal to 5. All right, here, subtraction is the inverse of addition. Okay, and along the same line, if I looked at 3x equals 12, I would divide by 3 to solve that. And you get x is equal to 4. Here, like before, we could say division is the inverse of multiplication. Okay, and this last example we have over here, x squared. Now this one, you might say, is an exponent. To undo this exponent, I would take the square root, because we see that the square root is inverse of squared. However, if I look at this last example, if I wanted to undo this x power, we really struggle with that because there's not an x root that we can deal with, right? And this is where logarithms come into play. Some things you may remember from previous classes, if I want to convert this to logarithmic form, I could say the log base 2 of 6 equals x. All right, and then this is actually our answer. The exponent that we're taking is log base 2 of 6. You can type this into your calculator, and you can get an answer of about x equals 2.585. We can actually think of logarithms as a function, right? And above we divided by 3, or we subtracted 2 to undo a thing. We can here do a similar thing. If we had 2 to the x equals 6, we can take the log with a base of 2 of both sides. Because what happens is on this left side of the equation over here, log base 2 of 2 to the x, because these are inverses of each other, they actually cancel each other out, and this just equals x equals log base 2 of 6, which we just saw was 2.585. Now we are going to, again, highlight on the natural base, and so if we have a function y is equal to e to the x, and we want to do the logarithmic form of this, or we want to undo something, we're going to be looking at the natural log of x. Now remember, I briefly discussed this before spring break, all right, but the natural log of x is going to undo exponentials with base e. All right, so we can see that down here with these few rules, right? If I take e to the natural log of x, that's just going to equal x. Natural log undoes the exponent, and vice versa. Natural log of e to the x equals x. They are inverses, and they undo each other. It's going to be our way to solve these types of functions. Now, a couple extra rules that we have with exponents, which are very similar to our, for logarithms, which are very similar to our exponent rules, are the following. Right? If I have log of x times y, here we have multiplication inside the logarithm, I can split that up as log of x plus log of y. All right, and all these rules can be done with natural log, and traditionally we do write them with natural log, so I will do that. This next one, all right, the next one says if I have the natural log of x divided by y, I can split this up as the natural log of x minus the natural log of y. All right, and then the last one is really just this first one repeated as many times as needed. If I have the natural log of x to the nth power, I can take this n and bring it out in front and make this n times the natural log of x. And this is going to be our number one most important thing we're going to use to solve exponentials of any base as we go forward. Okay, these next couple examples are just to familiarize ourselves with logarithms. All right, this is really going to be using some exponent rules with our few identity rules that we have above. Right here, I can split this exponent up as e to the natural log of 7 times e to the second. All right, this is our multiplication exponent rule. The reason I wanted to do this was this first piece here is actually equal to 7 using this first rule. The second piece is e squared. All right, you can actually evaluate this if you wanted to, getting a value of about 51 point, let's say 723. All right, but actually this here is a little bit more exact of an answer. Again, try this second problem over here on your own and check to the answer key that will be posted online. I also want to familiarize ourselves with some expansion. Just again, it's going to help us solve later on. All right, this natural log here, we can break up first and foremost and make it the natural log of x squared plus the natural log of y to the fourth. All right, and then we can use that third rule to make these 2 times the natural log of x plus 4 times the natural log of y. Okay, and that splits it up. Again, this is going to be a really important part when we get to what's called logarithmic differentiation. This makes differentiation can be a lot easier if you split up like this. Again, check the second answer or second question and check the answer online. One last thing we're going to do with the natural log and stuff like that is earlier, remember we mentioned that if I had a function like y is equal to 2 to the x, it's very difficult to take this derivative. All right, but using our natural log rules, so I can now write this as y is equal to e to the natural log of 2 times x. All right, and now this is a much easier derivative to take. This piece in the denominator, or in the exponent here, that's just a number. May not look like it, but that is some number. Natural log of 2 is actually about 0.7. All right, so it's a number, it's a constant, it's not changing. All right, so now we can take our derivative in a much easier way.